Hi, I have what I hope is good news for at least most of you. We're pretty much done with introducing new language features. We'll drop a few things on you along the way, but for the most part, the rest of the lectures will be devoted largely to how we go about building computational models that let us solve problems. We'll start with simulation models. For most of the history of science, theorists used mathematical techniques to construct purely analytic models that could be used to predict the behavior of a system from a set of parameters and initial conditions. This led to the development of important mathematical tools ranging from calculus to probability theory, and to a reasonably accurate understanding of the macroscopic world, but, as those of us who look at physics know, not really of what goes on, say, at the level of quantum mechanics. As the 20th century progressed, the limitations of this approach became increasingly clear, and people began to rely on simulation models more and more often. Simulation attempts to build an experimental device called a model. The intent of a model is to provide information about the possible behaviors of the actual system being modeled. Typically, in fact almost always, simulation models are descriptive, not prescriptive. They tell us how a system works under given conditions, but not how to arrange the conditions to make the system work best. Simulation models can be classified along three dimensions: deterministic versus stochastic, static versus dynamic, and discrete versus continuous. Deterministic simulations are completely defined by the model. Rerunning a simulation will not change the outcome. Deterministic simulations are typically used when the system being modeled is too complex to analyze analytically. For example, the performance of a processor chip. Stochastic simulations include randomness. That means that different runs of the same simulation with the same initial conditions can generate different results. Most of the simulations we're going to look at this semester are stochastic, for reasons we will be getting to in a subsequent segment. In a discrete model, the values of the pertinent variables are enumerable, for example, the integers, whereas in a continuous model, they're not enumerable, for example, the real numbers. Imagine, for example, analyzing the flow of traffic along a highway. We might choose to model each individual car, in which case we would have a discrete model. Alternatively, we might choose to treat traffic as a flow, where changes in the flow can be described by differential equations. This leads to a continuous model. All of the simulations we'll be looking at in this course use discrete models only. There are several reasons for the growing popularity of simulation models over the last decades. Most prominently, probably, is people began to get very interested in systems that were not mathematically tractable. For example, people became increasingly interested in the social sciences, e.g. economics, and creating models of those systems using conventional mathematics just did not seem possible. Furthermore, as the systems to be modeled grew increasingly complex, people really had an urge to find a way to model them in a series of successive refinements, where they would build a model, try it, discover they didn't like it, and then make it a little bit more accurate, a step at a time. You will see us throughout the rest of this class doing exactly that. We'll start with simple models, look at the results, and then figure out how to change the model to make the results more accurate. Another useful attribute of simulation models is that it's relatively easy to extract intermediate results. We can stop the simulation and look at what the world looks like partway through it. That, in turn, makes it easier to improve the simulation. And finally, there was a necessary condition, and that's the availability of fast computers and big memory. Until the advent of the modern computer in the middle of the 20th century, the utility of simulation was limited by the time required to perform calculations by hand or the mechanical complexity of application-specific simulators. One way to appreciate the pervasiveness of simulations today is to perform an internet search for various kinds of simulation. Let's go over here to my browser and give it a try. When I discuss this material in my live class at MIT, I always ask the class to tell me what they'd like to hear about. It being MIT, inevitably somebody says physics. So if we look at that, we'll see, well, there are quite a few, well over 6 million pages with simulations of physics. Increasingly, MIT students are moving towards the life sciences, so biology always crops up. Well, and we can see that appears, at least in this way, to be more popular than physics. There are always some finance students in my class. Not too surprisingly, finance in the world at large seems to be more popular even than biology. And then, even though nobody suggests it usually, I always do this because I love sports. And we see that sports are even more popular than finance. To recapitulate, simulation attempts to build an experimental device called a model. And I want to emphasize that it really is an experimental device. We run some experiments, and as with a lab experiment, we then end up improving it. The goal of the model is to provide useful information about the possible behaviors of the system being modeled. It's very important to remember that simulation models are only an approximation of reality. Some models provide better approximations than others, but one can never be sure that the actual system being modeled will behave in the way predicted by the model. Models provide predictions, and as we all know, some predictions are accurate and some predictions are not. In fact, it has been said that all models are wrong. That's the bad news. But the good news is that some are useful. In the next segment, we'll start looking at how do we go about building models that are indeed useful.